Welcome to solverfy.
Okay, so we have a square well with an infinite wall at x equals 0 and a wall of height u at x equals L. So for the case E is less than u, we need to obtain solutions to the Schrodinger equation inside the well and in the region beyond the well that satisfied the appropriate boundary conditions at x equals 0 and x equals infinity. So we also need to match the boundary conditions at x equals L to find the equation for the allowed energies. Okay, so let's start at the beginning. Inside the well, the particle is free. So in portion A, the particle is free and the wave function is trigonometric. So you'll get that inside the well, psi of x is equal to a sine of kx plus b cosine of kx. And this is for x between 0 and L. So at x equals 0, there is an infinite wall. This requires that psi at 0 needs to equal to 0. Therefore, b is equal to 0. Okay, outside of the well, so in portion 2, x equals L, u of x equals to u, and the Schrodinger equation has exponential solutions. So the exponential solutions, so this is for portion 2, your wave function is equal to ce to the minus alpha x plus d e to the positive alpha x. And this is for x greater than L. Okay, and we know that alpha is equal to 2m u minus e over h bar squared, the square root of this. Okay, so now we need to bind the wave function at x equals infinity. So to do that, as x goes to infinity, d will go to 0. So d needs to be 0. And at x equals L, you need it to be continuous. So this is where we will start to link the two equations. So we need continuity of psi and d psi dx. Okay? This gives us at x equals L a sine of KL needs to be equal to CE to the minus alpha L. So what we're doing is setting section 1 equal to section 2. Okay, this also gives us, so for the derivatives also need to be continuous. So Ka cosine of KL is equal to negative alpha C e to the negative alpha L. Okay, so the easiest thing to do would be to divide the two equations, and you will get K cotangent of KL is equal to negative alpha. So the dependence on E, you can see it if you show that K k squared plus alpha squared is equal to 2m u over h bar squared. Okay, so let's write this again. Now we have k cotangent of KL is equal to plugging in the value of alpha from above. It is equal to negative 2mu over h bar squared minus k squared all to the 1/2 power. Okay, so let's multiply L and square it. Okay, so we're going to multiply L, we're going to square it so that you can get L on both sides and we can get rid of this 1/2. But let's also use that cotangent squared, since we're squaring both sides. Cotangent squared of theta plus 1 is equal to cosecant squared of theta. Okay, so we multiply L by both sides and we square it. So we have KL squared cosecant squared of KL is equal to 2m UL squared over h bar squared. Okay, so we need to look at what happens for values of theta, different values of KL. Okay, so we can see that KL over sine of KL is equal to 2m UL squared over h bar squared, the square root of this. And this is the same as saying theta over sine of theta. Okay, so since theta over sine of theta is never smaller than 1 for any value of theta, there can be no bound states. So, no bound states if 1 is greater than 2m UL squared over h bar squared.